Hello everyone, we're going to be learning a brand new physics concept today, momentum. So today's lesson is just going to be an introduction and we're going to get into some more contextual examples next week. However, at the moment we're going to go through a few ideas on the board about what momentum really is. So, hope you're all ready to go because I've already got the first point up there. One of the most powerful laws in physics is the law of the conservation of momentum. So it's very important that we get our heads around this, because when we get our heads around what momentum really is, we start to understand why objects behave the way they do, why objects move the way they do, because momentum is associated with movement. So momentum, in simple terms, I'll just write it up on the board, momentum is the impetus, and I'll explain what impetus is in just a second, gained by a moving object. So there we go, we've got the word movement in there, so you've sort of got an idea that if an object was moving, it probably has momentum. But let's actually see what impetus really means. So, impetus is actually defined as being an impelling force. An impelling force means it causes an object to move. So let's say I were to push this whiteboard. I probably wouldn't want to because you would obviously not be able to continue writing down these notes. But if I were, I would be pushing a force into this object, and if this object were to move to the right, or your right, my left, then we would say that we are giving an impelling force and we're giving the object momentum because the object, the whiteboard, once I've given it this force, will have two things. And these two things are very important for an object to have momentum. An object has momentum when it fulfills these two requirements. So, because this is very important, I'm going to get out my blue pen here. And momentum is denoted by a P. So we write the lowercase p, and then we write mv. Momentum is the product of mass and velocity, and that's how we denote it in physics. Mass and velocity. So if an object has both mass and velocity, it has momentum. So this pen here, once I throw it, I'm not really going to throw it, but if I were to throw it, then it would have both mass, because obviously it exists, and we can feel it has mass. It probably weighs 30 grams or something like that. But if I were to throw it, it would have both mass and velocity because it would be moving. So now this brings us back to the idea of the conservation of momentum. So we've got this idea that that's the actual momentum formula, but why is this law that we mentioned up here so important? Well, to demonstrate this, I'm going to get out a mystery box item. So, I wonder what's in the mystery box this week. It's a Newton's cradle. The Newton's cradle is used to demonstrate many laws in physics. Today, I'm going to be talking about the law of momentum conservation. So I'm just going to pick up this ball, and I want you to think about the movement of these objects. It's quite interesting. In that collision there, they're passing on energy to another ball. They're passing on an impelling force to the end ball. Let's watch this again. I love the Newton's cradle, it's great. As you can see, pushing energy, and pushing that force along there, and it's causing the ball on the upper end to go up. So, if momentum is the product of mass and velocity, then what do you reckon's happening there? Well, in an ideal system, and that's what we generally talk about in physics, but in an ideal isolated system where there's no friction, there's no air resistance or other forces affecting us, then this law of conservation of momentum can be seen more clearly. The conservation of momentum means that if an object, in this case I'm going to stick with the Newton's cradle idea of object A, and we have a few more objects. But when it has a collision with object B, or another object, if it were to collide with it, then the momentum lost by A will be gained by B. Because momentum is conserved. Just like you've probably heard that energy is conserved. Again, this is the same sort of thing. So let's say that our momentum here, if we had a mass of, say, one of those balls is probably, say, 50 grams, for example, so it would be 0.05 in kilograms. And let's say that it had a velocity of, this is probably a bit high, but let's say it had a metre a second. Then the momentum that this possesses, and again, I'll go through calculating momentum in the next episode and what the units are, but the momentum that that object possesses would be passed on to B, whatever's lost from A. And in this case, you can probably see that most of the momentum, if we were to look at the first ball here, ball A, and if the others were to just stop for a moment, you can see that almost all of the momentum, pretty much all of the momentum is lost in the collision, but it's passed on. So that's when momentum conservation comes in handy. And one last thing I want to draw your attention to is the idea of impulse, because impulse relates to a change in velocity. So I'll switch back to a black pen now. And impulse is the product of the average force acting on an object multiplied by the time that that force is acting on an object for. So impulse gives us a change in momentum. Because again, when we have an impelling force, a force that causes the object to move, remember my pushing the whiteboard example, then we're obviously going to have a change in momentum. At the moment, this whiteboard has a momentum of 0 because it has no velocity. It has mass, but it's not moving, or it's not moving enough for us to notice it. And that, my dear friends, is momentum in a nutshell. There is one last thing I would like to do before I move on, and this is something you can actually think about for homework from this session, and that is the more complex momentum formula. So we simplified it to be the product of mass and velocity here, but the actual full momentum formula is the product of mass and velocity on the square root of 1 take v squared over c squared, where v is velocity of the object and c is the speed of light. The speed of light is 300 million meters per second. My question to you is, why does it not make a difference for most occasions if we were to use this formula compared to that formula? And my second question is, this is something for you to consider over the next week, do photons, or can photons, possess momentum? And that, my dear friends, is an introduction to momentum. Next week we'll be looking at the world's fastest bullet train, the maglev train, and they've got a new one that is expected to be released in Japan by the year 2027, and that maglev train can actually travel up to 500 kilometres per hour. We're going to be calculating the velocity of that maglev train, and then we're going to be able to calculate the momentum. Okay, so thank you very much for watching my video. I'll see you next week. Remember to do your homework, and I hope you've enjoyed this video.